Hey guys, welcome back. Think of me as your fun older sibling who's just here to make science a total breeze. Today, we're diving into a complete chapter explainer all about the absolute magic and mechanics of acids, bases, and salts. Now, if you've been struggling to remember all those complicated chemical reactions, or you just can't keep the differences between all the various sodas straight, don't worry. I've got you covered with some amazing tricks and practical examples that are going to lock this right into your memory for sure. Okay, let's dive right into this. Have you ever wondered why biting into a lemon makes your face completely pucker up because it's just so overwhelmingly sour? But then, on the flip side, if you've ever accidentally tasted soap while taking a shower, we've all been there, right? It has this really harsh, bitter taste. Well, that's not just a random coincidence. That is fundamental chemistry interacting directly with your taste buds. So to uncover these everyday mysteries, here is the roadmap for this explainer. We're going to start off by identifying acids and bases. Then we'll meet chemistry's detectives, the indicators. Next, we'll look at the magic of chemical reactions, explore the pH scale in our life, and finally, we'll hit the most crucial section for your exams, salts and their uses. All right, section 1, identifying acids and bases. Let's get right to it. Scientifically speaking, an acid is a substance that basically acts as a donor. It donates H+ ions, and as we just talked about, they have a distinctly sour taste. If you test them with blue litmus paper, they actually turn it red. Just think of red as a giant danger flag in the lab. Now, on the other hand, a base is a substance that releases OH- ions. Bases have a bitter taste, they usually have a really slippery or soapy feel to them, and they turn red litmus paper blue. So that sour lemon you ate, packed with acid, and that bitter, slippery soap, that's a classic base. And this brilliantly illustrates how we can actually easily remember the natural acids found in our foods. Memorizing these for exams can be super tricky, so I want you to use this fun mnemonic. Very acidic Orange City. Vinegar has acetic acid, and oranges or lemons have citric acid. For the rest of them, just imagine your friend asks you to play table tennis, but you really need to study. You tell them, TT tomorrow. Tamarind contains tartaric acid, and tomato contains oxalic acid. Seriously, it's an absolute lifesaver for memorizing these facts quickly and permanently. Moving right along to section 2, indicators, chemistry's detectives. Now, what's really interesting about this is that these chemical detectives, our secret agents, if you will, come in 3 distinct categories. First, we have natural indicators, which come straight from nature, like litmus, turmeric, and hydrangea flowers. Second, we have synthetic indicators. These are made by humans in a lab, like phenolphthalein and methyl orange. And finally, there are olfactory indicators. Now, olfactory relates to your sense of smell. These indicators actually change their scent to reveal hidden acids or bases. Common examples here are onion, vanilla extract, and clove oil. And these detectives work just like magic tricks. Take turmeric, for instance. Have you ever accidentally spilled some curry on a white school shirt? The stain is bright yellow. But when it's washed with soap, which we know is a base, that yellow stain suddenly turns bright red. It's wild. Synthetic phenolphthalein is normally colorless, just like water. If you put it in acid, it stays totally colorless. But drop it in a base, boom, it turns a vivid pink. And for our olfactory indicators, like onion or vanilla, if you add a base to them, their strong, distinct smells just completely vanish into thin air. Let's jump into section 3, the magic of chemical reactions. So one of the most classic chemical reactions is what happens when an acid meets a metal. When an acid reacts with a metal, it produces a salt and literally releases hydrogen gas. For example, when strong zinc metal is dropped into sulfuric acid, the zinc actually kicks the hydrogen right out, creating zinc sulfate and hydrogen gas. And how do we prove that hydrogen is actually there? We use the famous pop sound test. If you bring a burning candle near the released gas, it creates this very distinct sharp pop sound. It's awesome. But what happens when an acid meets a base? Honestly, it's literally like fire and water colliding. We call this a neutralization reaction. The acid and the base effectively cancel each other's extreme properties out to form a corresponding salt and water. This simple equation right here, acid plus base yields salt plus water, forms the absolute backbone of everything we are about to discuss next. But I'm going to let you in on a little secret. The salts created from these reactions aren't always perfectly neutral. It's kind of like a chemical tug of war, and whoever is stronger in the reaction dictates the final result. If a strong acid reacts with a weak base, the acid wins the tug of war, and you get an acidic salt. Conversely, if a strong base overpowers a weak acid, the resulting salt leans basic, giving you a basic salt. It all comes down to who's stronger. All right, section 4, the pH scale and our life. So this is the pH scale, and it ranges all the way from 0 to 14. pH actually stands for the potential of hydrogen. The number 7 is right smack in the middle. It's the neutral middle bencher, kind of like pure distilled water. Anything lower than 7 is acidic, and the lower the number goes towards 0, the stronger the acid gets. Anything higher than 7 is basic, going all the way up to a highly basic 14. So the really crucial point here is how these numbers relate back to the problems you face every single day. Take digestion, for example. Your stomach naturally produces gastric juice that is highly acidic with a pH of 1 to 3, just to break down your food. When you overeat and get an upset acidic stomach, what do? You take an antacid, like milk of magnesia. This is a base that literally neutralizes the acid. Or what about tooth decay? The hardest substance in your entire body, your tooth enamel, actually starts breaking down if the pH in your mouth drops below 5.5. That is exactly why your daily toothpaste is basic. It's there to neutralize those mouth acids. And if a bee ever stings you, it hurts because it injects a painful acid into your skin. The best home remedy? Rubbing basic baking soda right on it to trigger a neutralization reaction and cure the pain. And finally, Section 5, salts and their uses. These are the industrial superpowers. Okay, listen up, because this is an absolutely vital section for your exams. First up is an incredibly essential industrial process you absolutely must know, the chlor-alkali process. Here is exactly how it works, step by step. First, you take brine. Now, brine is simply a solution of regular sodium chloride salt mixed with water. Second, you pass electricity through this solution. The electricity actually causes the compound to break apart. Chlorine gas forms at the anode, hydrogen gas forms at the cathode, and finally, sodium hydroxide, which is also known as caustic soda, forms right near the cathode. It's literally just salt water and electricity magically creating 3 incredibly useful chemical products. Now, remember that chlorine gas we just made at the anode in that last step? Well, if you take that dry chlorine gas and pass it over slaked lime, it creates a brand new compound, bleaching powder, chemically known as CaOCl2. This powder is heavily utilized in the textile and paper industries for bleaching materials, and it actually acts as a super powerful agent for purifying our drinking water by killing off harmful germs. Let's move along and see how this builds, because I really want to clear up the confusion between 2 very similar sounding chemicals that students literally always mix up, baking soda and washing soda. Baking soda is sodium hydrogen carbonate. Notice the word hydrogen in there? Just think of it as needing water to bake. It's used in cooking because when it gets heated up, it releases carbon dioxide gas, which gets trapped in the batter and makes your cakes incredibly soft, spongy, and fluffy. Washing soda, on the other hand, is sodium carbonate that specifically contains 10 water molecules attached to it. It is heavily used to soften hard water, which makes it way easier to wash clothes, and it's a primary ingredient in the glass and soap industries. So they definitely sound similar, but their chemical makeups and daily uses are vastly different. Finally, let's break down plaster of Paris, or as it's commonly known, POP. You start with gypsum, which is a naturally occurring solid salt compound. Now, if you heat this gypsum very carefully at a very specific temperature, it loses some of its attached water molecules. Through this heat, it totally transforms into plaster of Paris, or calcium sulfate hemihydrate. This is the exact same magical material that is used to create those beautiful, intricate false ceiling designs in your house, and it's exactly what doctors use to create a hard cast to heal a fractured arm. Wow, we have covered a massive amount of ground today, right? From the sour taste of lemons all the way to the industrial chemistry used to fix our broken bones. But I want to leave you with a provocative question just to test your new knowledge. We know gypsum turns into plaster of Paris when heated, but what is the exact chemical difference in their formulas? Like, how many water molecules are we actually talking about here? Check your notes, do a little research, and let us know your answer down in the comments. Keep questioning, keep learning, and I'll catch you in the next explainer.